Welcome everyone. Please tell me what everything is good with the sound. Hi Artyom.
Hi, Alex. Hi, everyone. Can you hear us?
Yeah. I see people joining. That is amazing. So, that's Alex Voloshev and Artyom Chibatko, developer advocates at DataStax. And sound is good, amazing. Yeah, Katie, I made some homework as you see. I hope you did it too. So let's move on. So I'm Alex with DataStax. My job here is not let developers make mistakes and fail with Apache Cassandra and distributed systems in general. And that's Artyom. Artyom, could you introduce yourself?
Yes. I'm developer advocate. My main interest in data modeling, data quality, but I also love data warehousing, work with SQL databases as well. But over my career, I've been working with pretty much every major type of database: relational, XML, RDF, graph, NoSQL, different types of NoSQL, and so on. And I'm happy to join this workshop to talk about data modeling for Apache Cassandra. There will be a very cool demo later. Hope you will like it.
Yep. We DataStax developers, we know whom to invite for each workshop. And Artyom is the person who developed a data modeling methodology for Apache Cassandra. So on all of the world, he is exactly the right guy to talk about that. Good. Today we will use GitHub repository as the last time. You've seen that. We will do some practice scenarios with ASTRA. And for data modeling, we will use a special tool developed to make your life easier. Before we proceed and to let everyone jump in, please jump in on Mentimeter and answer our questions. First question will be to understand your experience. How much SQL experience do you have with relational databases? If you attended our last workshop, you already know what to do. Just go to menti.com and use the code 14095206. And it's not Mind, but Mentium. Menti. But link is on the screen, menti.com, and code is on the screen too. I see we have some experts, which is good. Okay, more people joining. Let's jump to the next question. How much NoSQL experience do you have? Okay, a little bit. That's a good place for you to be. NoSQL a lot. Good. No prior experience. Also nice. So don't forget, NoSQL is very different. So your knowledge of Mongo will not help you with Cassandra, and your knowledge of Cassandra will not help you with Neo4j. Those are different tools for different use cases. And today you are going to improve your knowledge of one of the most powerful and most scalable of the NoSQL databases. Good. Then let me check. Are you into the topic already? NoSQL databases are schemaless, correct? I love asking this question. No. Okay. Will anyone answer yes? Yes. Okay. Someone. Okay. Looks like someone missed our first workshop. Not all NoSQL databases are schemaless. There are plenty of schema-full NoSQL databases. So the correct answer is no. And I see most of you know that already. Isn't that amazing? We have some people of experience here today. What about normalization and denormalization? Do you know what is that? Do you know when to use it? Do you use it all the time? Okay, some people understanding that, or at least basic understanding, very well. If you don't have, don't worry. We will briefly explain it today because normalization and denormalization are very important techniques to learn, to master if you want to be good engineer, if you want your applications to be quick and efficient and your customers to be happy, you totally need to know and understand both techniques. We were taught what denormalization is bad, and that's why I have to ask you, what about denormalization? Is it an absolute evil, or there are scenarios where it can be good? Skip question is totally fine because we will explain denormalization foundations today. So take a look, Artyom. We work with pretty experienced audience today because on most of our workshops, then I ask this question, what people answer? No, denormalization is an evil. Denormalization is bad. Yeah, denormalization can be good. Absolutely. As long as you control it. Don't let denormalization control you, you know?
That's
so
right.
you are the engineer. You have to stay in control.
There are certain things we will talk about denormalization that's certainly useful, but you need to be aware of the drawbacks as well.
Good.
Like data duplication, yes.
So all the latecomers have joined, judging by the stream viewers, so we can proceed. Again, thank you everyone for joining. That matters a ton to us. Today we will speak about data storage, organization and distribution in Cassandra, because that's what something makes Cassandra so special. Very performant, but also with some sharp edges you need to know not to hurt yourself. Then we will speak about keys and how keys are so important, how keys define so much. We will speak about SQL data types, not in big details, but we want this workshop to be 2 hours, not 2 days, okay? Then a lot of attention to data modeling process because it's the most important part of the day, optimization techniques, and basically what's next, homework, and so on and so forth. And we will start with data storage overview. So, data distribution. We discussed it briefly last week, but I see some people still not completely getting into that and how important it is. And maybe there are some newcomers today. Cassandra keeps data distributed. It means what the same pieces of the same table will be spread over multiple servers. Servers keeping your information are organized into so-called rings, or you can also call it just a data center. And those data centers combined together will build a cluster, and this cluster can be geographically distributed with all nodes active, where no idea like a slave node or a secondary node, forwarder node, each node can process each request globally. There is no single point of failure. It scales perfectly for write applications and for read applications. And your app can contact any node, switch to next node, work with next, again switch to next data center if required. It's totally possible, and that's what makes Cassandra globally available and highly available. Data in Cassandra is organized as tables, and those tables have strict schema. That's still NoSQL. But those tables are distributed tables. So data of these tables are spread across the cluster, across your data centers. And there is no single node which hold all of your data. Cassandra is ready to work with data of any size, and that means petabytes, literally petabytes. And petabytes, ladies and gentlemen, that's a lot. So, how it works? Quick reminder. Then you arrange a partition key. We will discuss it in details today. Then data arrives on a node, or basically even earlier actually, when your driver starts the operation, Cassandra driver in your application starts some operation to write or to read, it will get a partition key and hash it to a token from string or from whatever value into an integer value using some special hashing algorithm and get a token. Per table, each node owns a range of tokens. Numbers you see on the screen 0 to 16, 17 to 32 and so on. You actually, yes, those tokens are like those numbers, but much, much longer, of course, because there could be billions of partitions. And then data is not only partitioned, but also replicated as many times as you define in replication factor. So you see these data on the left bottom part are exactly the same rows, exactly the same partitions, but they're stored on the multiple servers because your customers want your application to be always available, and that's what Cassandra does. Data organization, we briefly discussed already. So data organization, organized cell, included into row, into partition, into table, into keyspace. Keyspace is a logical group of tables and some other settings, user-defined types, grouping it all logically. Tables organized into rows and columns, and groups of related rows called partitions what are stored together, and that is a very important feature for both good and bad, for restrictions and for power. Each row contains a partition key. You cannot store data without specifying a partition key. It's technically not possible. Cluster will just not know where to put your data. Starting working with Cassandra, first thing you have to do is to create a key space. How do you create a key space? Very easy. Here you see SQL statement, Cassandra query language statement. What creates key space, and Cassandra query language is designed specifically to be as close to SQL as possible, to be just more familiar to every developer in the world. Then you create a key space. You have to specify its name, quite obvious, but that's typical for any database. But also you have to explain replication. You have to tell cluster how do you want it to handle this data. You have to define a replication strategy class, and you have to define replication factor. So replication strategy class is a very, basically you have two options: network topology strategy and simple strategy. So not a lot of choice. Simple strategy is good for your laptop and bad for anything else. You use simple topology strategy, simple strategy for your laptop, for development environment, maybe for test scenarios, maybe some for development environment, maybe it's for some kind of development servers, but you definitely don't go to production with simple strategy. Network topology strategy is vice versa for production placements and for your staging maybe environment, because it's a very cool advanced strategy. It does really a lot of work for you. Take a look on the lines for the data centers. Here you see United States West 1, Europe Central 1. Those are data centers, names of your data centers. For different companies, you will have different data centers names, right? And you say what for United States West 1, I want to have replication factor 3. For Europe Central 1, I want to have replication factor 5 for whatever reason. And here comes network topology strategy. What it does, it takes your replication factor, define it, and puts the data in the way what it will be located within single data center, but on the multiple different server racks, or if you use clouds, so it will be the same region, for example, United States West 1, but different availability zones. You understand why it's happening? Again, your customers want your application to be available always. When we use network topology strategy, it's a very advanced thing what takes care of keeping your replicas not together, but as far from each other as possible within one data center or region. Why it matters? The story is availability zone of a cloud provider can get down. If all of your replicas were within this availability zone, what will happen? Your data will be unavailable. Same happens with your data center. In the data center, you have multiple server racks, but servers within single server rack are also vulnerable to the same issues. For example, if power outage for a single server rack or network outage, the whole server rack will become unavailable. So you need to have your replicas on the different server racks or on the different availability zones of the cloud. And that is very important. And network topology does it for you absolutely transparently, so you don't have to take care of that. Isn't that amazing? Then, very common misconception, what I see very often is what people start to do weird thing with their replication. They try to define all the data centers they have in the list of this replication story. But that's not exactly right. Take a look. I can have a dozen of data centers all across the world. Europe Central 1, Europe Central 2, Europe East 3, whatever, I don't know, Asia, and so on. You don't have to specify all of them here. Here you specify only data centers, what you want to take care of this data. For this Keyspace, it will be United States and Europe. For another Keyspace, for example, I don't want to keep data anywhere. I need it only on Europe Central 1, so I don't specify US West, and I have only data replicated to a single data center. Well, it decreases availability of the data because availability will be then available to only one single data center. So you may have to consider different scenarios for different kinds of data you are working with. That must be quite obvious. When we create a table, we have to specify key space we are going to use, table name, also quite obvious, columns with their types, and we have to define primary key, which consists of a network of partition key and clustering columns. Those are extremely important, so we will speak a lot about it today. That's a much more advanced thing and very much more important thing than you use it to think in relational databases. And here we go, Artyom. Let's create database we will work with. Maybe you have it done already.
Yes, so we will create a new database in AstraDB. If you already have created the database previously, then you may need to create a new key space, or maybe you already have it from the first
you sharing
part
your screen?
of this.
Sorry, are you sharing your screen?
Yes.
Yeah, because I see the slides, but we will need your screen, I guess.
Okay. So to start, you will have to go to the link that is on GitHub. You can see it in the chat. So it's a link that will bring you to this web page, README file. And here we will be creating new AstraDB instance or using the previous one. So this is, sorry, didn't work as expected. Okay, so we're going to create a new AstraDB instance. What is AstraDB? It's a cloud service, cloud database service that is built based on Apache Cassandra. You can click the Create AstraDB and you will have a screen where you will be able to either sign up or sign in. I'm already signed in into mine account, and I have some other hibernated database here, but I will create a new one following the instructions. So I will click Create Serverless Database, and we'll create database called Workshops. And the Keyspace name that we want to use, and you already know what Keyspace is, Alex talked about it just recently. So it's going to be sensor underscore data. Okay, we also need to select the provider and region. We are going to use Google Cloud, and in my case, it's going to be North America, and I need to select one of the regions that is not logged. I'm also using free account, just like you. So in this case, this is South Carolina. and I can click create database, and it will take a couple of minutes to get created, so we will be able to use it later for the next lab. But at this point, it's finishing up. Okay. Well, it says it's the status is still pending. So we will wait, and while we waiting, we can continue with the next topic. Okay, so the next topic I will talk about key definitions, and you've already seen some of those things, but we will still repeat what is primary key, what is partition key, what is clustering key, because this is essentially very, very important and essential for schema design, right? And schema design is part of the data modeling process. So this table in this example that you may seen already in the last workshop, we have primary key definition here that consists of partition key and clustering key. So the role of the partition key is to uniquely identify a partition within a table. But also, as you know already, that partition key is responsible for data distribution strategy. So it defines which nodes and replicas will get that particular partition, will store it and will serve it, will retrieve it, send it back to the application. Okay, so how you define partition key will define not only uniqueness of that partition, but also how the data will be distributed. And that's very important. So in this example, where we have sensor as a partition key and timestamp as a clustering column, okay. In this case, the sensor ID itself will define the partition. And in other words, all data that generated by that sensor will be stored in that one partition. But if we look at the last example where we have sensor and timestamp together, this is composite partition key, then in this case, since sensor and timestamp will always be unique, each sensor generates only one value for a given timestamp, then each partition will essentially contain just one single row. Okay, while in the first example we have multi-row partitions, here we have a single row partition for the example where we have both sensor and timestamp as a partition key. Now, besides the partition key, primary key consists of optional clustering key, or sometimes we just say clustering columns. And the purpose of clustering columns, so if you have clustering columns or clustering key, then your partition can have multiple rows. So it's a multi-row partition, and clustering key uniquely identifies a row within a partition. So that's one purpose, to ensure uniqueness of that row within the partition. But the second purpose is also sorting order. So as you know, tables are stored as tables internally, so they are sorted strings. How they are sorted? They are sorted based on clustering columns. So it's clustering columns will define the physical ordering on disk, and when you retrieve that data, when you retrieve that partition, you will be able to get that order that you specified, or you can reverse it. So if you need your data sorted, you need to think about clustering columns, how you use them, and whether they will be, what kind of clustering order you will use, whether it's descending or ascending.
I want to step. Sorry, I want to step in here for a moment regarding sorting.
Sure.
Yep. So the story is then coming from relational databases, you use it to be able to sort data by any field, You use it to be able to filter data by any field, and you take it as given, which is not always correct. So we work with data of very different sizes usually. We work with data distributed over hundreds of servers over multiple continents. And the long story short, sorting data of this size over multiple servers, over multiple continents is totally not easy. But still, Cassandra can return your data sorted extremely quickly. How it happens? That is a part of our course at the academy.datastacks.com. It's a free course, so it's not really an advertising for it, but yes, it is. Despite it's free, it's also very important for you to get this one, to get real understanding and get ready for the certification for Apache Cassandra, which DataStax sponsors. So with us, you can get certified in Apache Cassandra totally for free. Now, getting to the sorting part. Clustering columns are very important because they define the sorting and the way how data will be stored on write time. So when you are going to retrieve this data on read time, it will be sorted already and there will be no need for Cassandra to change anything. As it's sorted already, just return this data back and we are done. So good thing, it's even for sorting extremely quickly. Bad thing, you can sort data, as you will see soon, only based on the clustering columns. You cannot sort in this case. In this example, you cannot sort data by value without using some nasty hacks we recommend you not to use.
Right. And it's important to remember that sorting is defined within a partition, not within the whole table. So if you're going to retrieve more than one partition, then the sorting order is going to break. So, but if you retrieve one partition and you have clustering key there and clustering order defined, then you will get the rows in that partition within that partition sorted. So in this example, of course, every time we design primary key, we're thinking about how we're going to access data, how we're going to query it, and design our table and primary key based on that query. So in this example, if we say that sensor is the partition key, there is no clustering key, and we try to store temperature value, some kind of value that sensor generates, then each time we will add that, we will write into that table for that sensor, we will basically absorb the previous value because there is no clustering key, nothing to distinguish. The rows are not unique, so each time, so it's basically a table with single row partitions. For each sensor, there is only one partition with one row there. So this is not going to be a good design if we try to store values. If we try to store, if you also, for example, our query would be store all the values generated by, or retrieve all the values generated by a sensor and filter that based on dates. For example, specify the date range, how you want to retrieve that data. So in this case, if we add timestamp to this primary key as a clustering column, then we kind of solving the problem of uniqueness, because now each sensor can only generate value with unique timestamp, and then the next value will have a different timestamp. So in this case, we guarantee that we will not have absurds, but it's a little bit harder to retrieve that data based on date. It's still possible. You can replace date with timestamps, but it may not be the 100% easiest solution. Now, the third example here is not good because we also add in value into this clustering column. So you can think, so the value, so all the data generated by a sensor will be sorted based on value first and only then based on timestamp. So we will not be able to, uniqueness is there, but we will not be able to filter based on dates correctly. And then the last one is probably the best example for this particular query, we are going to retrieve data for a particular sensor, do the range search on dates, and timestamp is there to guarantee uniqueness. Okay. So together, the primary key consists of mandatory partition key and optional clustering key, but together primary key gives you uniqueness of a row within a table, right? Remember, partition keys uniquely identifies partition within a table. Clustering key uniquely identifies row within a table, and a row within a partition, and primary key uniquely identifies row within a table. Okay, so partition keys, like we already talked about, they define data distribution of a cluster. That's important to remember. So you will need, when you design primary key, you need to design it for specific query. So for example, support retrieving data based on sensor ID and date, but you also need to think about how that data will be partitioned based on that specific partition key. And clustering columns, like we said, they define how the data is sorted on disk, literally physically, so you can retrieve in that order, or you can reverse that order. So for this example, where we have primary key that consists of partition key, sensor, and date, and clustering key timestamp, what types of queries we can do over this table? We cannot, for example, retrieve data for one particular sensor, because we cannot query based on partial partition key. So we will have to specify both sensor and date. We cannot do the sensor greater than something. We cannot use partial partition key, a subset of partition key. We cannot ever use inequality, like greater than, on a partition key column. So that's not going to work either. Even here, we're using sensor and date together. Inequality is not going to work. So types of queries or predicates we can define. Here, for this specific primary key, we will have to specify sensor and date, and we can also specify timestamp using either equality or inequality search. Okay, so the one of the consequences of defining your primary key the way you define it, besides the data distribution and sorting, will be CQL queries. What types of queries you can do? Okay. Another consequence is schema immutability. Once you define your primary key, you cannot change it. You cannot just alter that key. You can add some other columns that will not be part of the primary key, but the primary key is something that you do not want, you cannot change, and there is again a good reason for that. We're dealing with large data set that is spread over multiple nodes, across many nodes in your cluster, and possibly multiple data centers that communicate over network, and they may be in different parts of the world. So in that case, if you change the primary key, then you will basically have to redistribute your data, right? Basically, you change and redistribute and sort it differently, possibly. So that's not a good thing to do when you're dealing with large data sets. So if you do find yourself needing to change something in primary key, you will have to drop the table, or you will have to create a new table first with new primary key, transfer the data, and then drop the old table. But usually you want to design your table correctly right away. Now, a question that we frequently get is, why don't we use sequential IDs in Cassandra, something like auto increment? And again, this is actually not a Cassandra thing. This is any distributed system saying that it's not easy to maintain that sequence, because you have multiple nodes in your cluster. Each one can generate a new ID, and if you want the sequence, then all of those nodes have to communicate to agree on the next available ID to use for when you insert in the row. So in MySQL, for example, you can use auto increment, which is sometimes convenient. It's artificial surrogate ID, which just generates a sequence of numbers. But in case of Cassandra and most distributed systems, we're using UUIDs and time UUIDs. So those are two different types of UUIDs, and essentially any node can generate that UUID, or your application can generate that UUID very quickly, efficiently, and guaranteed that there will be no conflict between those different IDs generated by different nodes. Okay, so and the next topic, the rules for good partitioning. I don't know if Alex wants to.
Yep,
Talk about
I
it.
would love to. It's one of my favorite topics, you know. So give me a moment to switch back to myself. Big display, big boom. Yes, we are good. First of all, I had to ask, are you guys listening as well? Because I see in the YouTube chat some people are mentioning buffering. I don't know on which side it is, because YouTube shows me excellent, stream status excellent, all green, all positive. Streaming software shows me some minor issues. So if you can hear us, oh yeah, it's bearable. Thank you, Sumit. So let's proceed then. Good. So, three very important rules of a good partition, just three, so it's easy to learn them all, but very important to follow. We will work on this example, which is familiar to you already. We will work with a table of the data temperatures by sensor. Table definition is quite simple. We store sensor, date, timestamp, value, that's it. So text, date, timestamp, float. Solve it. But working with Cassandra, you should not forget what, although a wide part of the table, amount of columns may be low, amount of data in this table can be extremely big, like very, very long. So let's take a look at few things. Store together what you retrieve together. Avoid big partitions. Avoid hot partitions. Only three things you have to remember, but you have to remember it very, very well. Let's take on the example when there do not store together what you retrieve together. If, for example, we make a partition key, you see in this case both sensor and timestamp will be parts of a partition key for this table. What will happen then? We will have as much partitions, as much records we will have, because sensor ID, which is always the same per sensor, and timestamp, which is always new per record, timestamp will be changing all the time. They will be hashed together, and as a result, you will have cache always new. And you will have as much partitions, as much records you have. Is that bad? By itself, it's not bad. In Cassandra, you can have as much partitions as you would like to. Not a problem. What is the real problem then? Real problem is on the retrieval time to get all of the data for last week. For example, you want to see a temperature of a sensor X for the last week. Sounds like a reasonable query, right? But what will happen on the execution time? Then you execute this query. Don't forget, querying data, we have to give all the parts of the partition key. That means what to retrieve data, we have to specify sensor ID, which we know, mostly probably, and timestamps of all the records. First of all, we don't know them. But even if we know them somehow, magically, then as those are different partitions, they can be stored on different servers. And therefore, we will have to reach as much servers stores your data, and that is as stupid as it sounds exactly. But there is a second example, which is much better, still have some problems to be discussed on the next slides, but already much better. Sensor as a partition key and timestamp as a clustering column. What it gives to us? First of all, data is grouped by sensor. That is good, because if I want to see data for sensor X on July 6th, I have to specify sensor ID, which I know, and then as timestamp as a clustering column, I can use inequality predicates. I can say like before 6th of June, like after 5th of July, before 7th of July, which will be my perfect 6th July, for example. On the partition keys, on the previous example, I cannot use inequalities. So I cannot make a range bigger than, lesser than, if we go with a primary key like this. So this one simply will not work. In this case, we have data grouped by sensor and ordered by timestamp. So boom, it's now solved. And that helps me to keep my data together and retrieve that together because it's always stored on the same server. We discussed that, Virash. Thank you for a good question. We discuss it soon. Then, second question, avoid big partitions. First of all, don't forget why do we do partition after all? Why partition data? We partition data because sharding is very painful and hard, and we want to avoid sharding. So we work with a data of a big size, and we split this data into chunks, partitions, so they always will be handleable. But then you do too big partition grow, what happens next? Boom, you have the same problem like you are trying to dodge just before it's your partition too big, not the whole table, but the consequences are exactly the same. Your database will be slow, it will be hard to impossible to maintain it, and so on and so forth. So we really have to think of how much data you will have per partition. There are only one hard limit. You cannot have more than 2 billion cells per partition. So intersections of columns to rows. But this is only hard partition. Our hard limit, our recommendation, soft limit, is not to have more than 100,000 rows in a partition, or a partition to be a size of more than 100 megabytes. Now, how do we control it with our partition keys? Partition key can be composite or compound. And that means what we can include multiple different columns in the partition key. You need to keep it under control, because don't forget, there are two ways we access data: when we write and when we read. When we write data, we can put to partition key basically whatever we prefer, whatever we know about this piece of data. Will it work? It will work. We will have small partitions. But then on the read time, what will happen? We will again have to give all of everything what we put into a partition key, and there's no going to be a lot of fun. So we need to keep our partitions small, but not too small, otherwise we will have problems reading it. Let's take a look at the first example. Sensor as a partition key, timestamp as a clustering column. And you may be now like, what? Wait, Alex, you just told us previous slide what that is a solution. That is the right approach. Like you remember previous slide, store together what you retrieve together. You group data by sensor, sort by timestamp, and you are good. Is that right approach? There is a checkbox, but it's gray, not green, because it is the right approach, but you can have different scenarios, and that's not always the right answer. Take a look. If you have your data written once in a day, once in a week, once in a month, then this approach can perfectly work grouping by sensor, partitioning by sensor, because you have your data once in a week, then therefore in a couple of years you will have like 100 and something records. In 6 years you will have 600 records per partition. It's totally fine. But imagine you have your records storing every 10 seconds, 5 seconds, every second. That's also happening in IoT world, totally. What will you do then? Your partitions will grow over time. So then you store all the data for a sensor, storing it every second, and your sensor runs for years. What will happen with this partition over time? Nothing good will happen with this partition. Cassandra has some tools to discard old data, so-called TTL, time to live. So creating a record, you can specify, I want this record to be automatically deleted after 1 month. But what if you want your data to be available after years? For example, you have strict audit requirements from government or whatever. So you have to store data for a long period. You cannot delete it with time to live property. But we still have to handle it somehow. Very easy. We make this compound partition key, which stores sensor and also some value depending on the period you want to store data in a group. It can be hour if you have really a lot of writes per sensor per second. It can be day, it can be week, it can be month, it can be year. It depends on the amount of writings per this period of time. In this case, for example, I want to group them by month. Remember, bigger the partition, easier to read, but it will cost you a lot if partition becomes too big. So don't make partitions too small, it will strike back on the read time. Keep them reasonably small, and we recommend to stick to 100,000 values in partition up to 100 megabytes in partition. In this particular case, I don't care about the size, because the data we are working with is text, date, timestamp, float, so each row will have really small footprint. But in general, the amount of rows can definitely become a problem. Bucketing is usually, it's called when you use a totally artificial key for grouping. In this case, month, like for example, that is a July of year 2022. This month value can be string, can be integer, doesn't matter, will be 202207 year 2022, 7th month. And that's not totally artificial because it comes from timestamp. But it's also not like we usually speak about bucketing. Okay. And finally, avoid hot partitions. That I have to give credits. A totally great example introduced by Cedric Lundven. And Cedric, thank you. It's much better when it was before, really. Primary key, date, sensor, timestamp. In this case, as you see, we use as a partition key what? Date. And that brings to interesting consequence. It's very easy to get information for each sensor for this particular date. Today is 27th of July. So I want to see data of all the sensors for 27th of July. With a table partitioned like that, I can do it with a single query reaching single server. So read time can be extremely efficient, right? But take a look what's going to happen. You know what Cassandra scales very well. I told you. And there was a little mark, like it depends on your data model. Last week, maybe you remember that. Now take a look. You have 100 servers. You store a lot of data. And you have a table like that. Over time, if this model doesn't work very well, your servers are overloaded, there are too much of writes. And you think, hey, Cassandra scales so good for writes, I will simply go and add more servers. I have money, I can afford it. I will make these 200 servers. I will go and buy 100 more servers. What's happening then? Now you have 200 servers. Did it help? No. No, it didn't help. You can buy 1000, it will not help. Why? Because data is written to servers responsible for this partition. With replication factor 3, you will have 3 servers responsible for this partition in this database. With a huge amount of writes, that will be basically one single partition active all the time. There will be no partition, the partitions will be more or less even. So partition for today, partition for yesterday, they will be overall of more or less the same size, but workload will be different. Servers responsible for yesterday partition will be idling, and servers responsible for today partition will burn in hell just because your data model was not good enough. So think about it. Don't be rude to your servers. Take care of them like they are good. They deserve some good attention. I tell you as an operations guy. Now, take a look for the second example, which is significantly better. If for you it's important to group data by date to be able to see all of the data with one single fast query, then this design totally makes sense. You group data by date and sensor. So therefore, partition, you will have different partitions per date, per sensor, and it will be never too hot because a big amount of partitions will be distributed over all of your servers. And in this case, if your cluster is overloaded, you can buy new servers, bring them to the cluster. What will happen? Token ranges will change. Each server will be responsible for less amount of partitions, and you have a smaller workload per each of them. So here scaling of Cassandra comes. But scaling of Cassandra is a shared responsibility. It's not only Cassandra does it, but you have to think about it in advance designing your data model. And Artyom, we are done with this page. If you want to add something, that's fine.
There are a couple of good questions.
Okay, let's
one
shoot it.
question, and both of them I think from Viraj. The first question, for the use case, for the example, when we use sensor and mons as a partition key, he asks, so for the current mons, that partition will be hot versus for the previous months, nobody is gonna use those partitions.
I believe, I believe I answered it in the end. The story is not, the story is not to have overloaded partitions. As long as your partitions are small, you can scale. You have high load, you add more servers, your data being shuffled to them, and less workload on the server, everything is good. The big problem, much bigger problem, is then you have uneven size or uneven workload on the partitions. When all other partitions are idling and one partition is too hot for a single server to handle. Don't forget, partition is a base unit of access. It's something what you can pick up and put to a different place. As long as your server can pick up single partition and put it to a different place, you are good. Then it's when it has multiple heavy partitions, you can put it to different servers. But when you have one huge or one which is being overwritten all the time with billions of requests per second, then obviously there is no server to handle that. You want to add something?
Yeah, I think there could be, I don't know if it's maybe something that is not obvious. So yes, for the current months, there will be more access to those partitions, but months is not the only column in the partition key. The sensor ID is also there. So it's not like okay, for January, all the partitions will be on this node because the sensor will also change the partition key. So for the partitions for January will be distributed across all the nodes in the cluster because the sensor IDs will be random and things like that. So there should be no problem with having load very high on one specific node or a few of the nodes. If, of course, you using the sensor IDs are more or less randomized, and there is no a subset of sensors that are generating more data than others and things like that. And there was another question about the case when we have something like users who are following other users, or they
Social
connect to
media.
other users. Social media, yeah.
Yeah.
So in that case, if you have a celebrity, there are so many people following, so you will have millions of people, millions of rows for that person, for that celebrity, and followers of that celebrity. And this question is actually so great because it gives us the next lab that we are going to do right now, lab 2, is going to talk about dynamic bucketing, specifically for this use case. And we're going to talk about sensors, but you can imagine instead of sensors by network, it's the same thing would be followers by user, something like that. So let me.
So we are switching to, oops, wait a second.
Yes. So it's a second lab on GitHub.
Let me switch to your screen. Wait a moment.
Yes, please.
Yep.
Okay, on GitHub we have number 8 here in our README file is dynamic bucketing. So what is dynamic bucketing? So let's look at, based on this example, we have a table that supports query find all sensors in a specified network. So given the network, so we are going to group all the sensors over a given network. So we will have to use network ID or network name as a partition key, and sensor ID will be clustering column. So this table only has 2 columns, both of them part of the primary key for simplicity. But what it means, for the network partition, we will store all the sensors. And it's like we'll store all the followers of a user. Right? In this case, some networks may have just a few sensors or dozens of sensors. So the partition for those networks will have dozens of rows, which is not a big deal. But maybe some sensors, maybe within a city, region, or something, they may have thousands or even millions and tens of millions of those sensors. So we do not want the partition to have millions of the sensors stored. So the key attributes of the problem that we are trying to solve is that the number of rows in a partition can be dramatically different. So in one case, we can store everything in one partition. For another network, we will have to create 10 partitions. But for the third network, we may have to create 100 partitions. So it's going to happen dynamically. And maybe we keep adding more sensors to the network, or maybe our sensors are actually mobile, and my cell phone is a sensor. So once I move to a different location, I'm joining different network. So there is dynamics there. So we will store, so that we will use dynamic bucketing, and we will store our sensors inside of buckets. And buckets is essentially artificial surrogate partition, and we will assign those buckets to each network. So some network may have only 1 bucket, another network may have 2 buckets, 10 buckets, another one may have 100 buckets. So we will need 2 tables for that, and I'm going to explain you how it works first, and then you can go to AstraDB and work and basically try this example there. The first table is going to manage buckets. So for each network, we will have a list of buckets. And so network will be partition key, bucket will be clustering column. What's important to notice here is that bucket is time UID. This is important because so UID gives us easy way to assign unique IDs, but time UID also allows us to sort those buckets based on time component of the UUID. So why is it useful is because when you want to add new sensor into a bucket, you want to retrieve the latest bucket, the bucket with the highest timestamp, and that sorting order will allow you just to retrieve one bucket for that network, just the latest bucket. So limit one, we will see how it's done, and it's very convenient. So time UID is better than UID in this case. And then the other table is going to store sensors in those buckets. And you can see network is not even mentioned. So there is a networks have buckets, buckets have sensors, right? Very simple design. Bucket is partition key, sensor is clustering key, okay? And at this point, let me actually go to AstraDB, a new, okay, stay logged in, I'm on time. So we created here our database, which is workshop database, and has Keyspace sensor data. So I will use SQL console, and we'll say use sensor data. So I will select my Keyspace that I want to use for this lab, and I will copy this definition of two tables, and we insert in some sample data. We insert in forest network has two buckets. One starts with 4, another with 7. And for each of the bucket, we will insert some sensors. So there are 2 sensors in the first bucket and 1 sensor in the second bucket. So the IDs here are just regular strings, easier to read. Okay, so let's create these tables, insert some data. So now what? We want to know how to use these 2 tables now. And specifically, we want to be able to add a new sensor to a network. What happens in that case? To add a new sensor, we need to first decide which bucket to use. Okay, which bucket to add. Maybe there is only one bucket, but maybe there are multiple. So we will first select the latest bucket, the bucket which was created the most recently. How do we do that? We simply select the bucket from buckets by network, where networks equals forestnet limit 1. Remember, our bucket ID is time UID, and its clustering key and its clustering order bucket descending. So it's ordered based on the time component of the time UID. So we will get the latest one by just retrieving one row from that table. Let me do that. Okay, so this is our latest bucket, and we can actually verify that that it has its time component is higher, timestamp is higher than the previous one. We don't need to do that, however. So then what's the next thing? We want to find out whether this bucket is full or not. So we will count how many rows, how many sensors we already have in that bucket, which is very simple. Create it again. So we only have one sensor. That's the second bucket. The first one we have 2 sensors. The second one we have 1 sensor. So at this point, your application logic will decide whether this bucket is full and we need to create a new bucket with generate new time UID and insert into new bucket. Or if it still can hold additional sensors, in this case, it can. We simply insert into that bucket. This one. We simply insert into that bucket the new sensor with ID S1004. Okay, so quite straightforward. Now we added new sensor. How about we retrieve? Remember, the query that we needed to support is to get all the sensors for a given network. But we, again, need to first retrieve all the buckets for the given network and then retrieve the sensors. So this is we retrieving all the buckets, get all the bucket IDs from bucket by network for specific network. Okay, and we have only 2 buckets. You can notice the ID 7449, and this is done within your application. So the next step, we will retrieve sensors from both of those buckets. So where bucket in 7449, and we will be able to get all 4 sensors in our result. So to finish this lab, what I want to say, the dynamic bucketing is extremely powerful mechanism that you can solve all kinds of problems with big partitions and hot partitions dynamically. But of course, if you introduce new buckets, they correspond to partitions and your access pattern changes. You have to query multiple buckets or multiple partitions. Like in this example where we use bucket in, we basically accessing 2 partitions. Querying 2 partitions is slower than querying 1 partition, right? Unless we are splitting very large partition into 2 partitions, right? In that case, it's better to query 2 partitions because you basically, your workload distributes better, right? You using more nodes to access that large partition. Okay, do you have any questions?
Looks like I don't. Nope,
I don't.
nope, we are good, we are good.
Okay, so in this case, we can continue, and Alex, the next part is still your part, right?
Yes, as far as I remember. So, the only thing I wanted to add is I see in the slides, in the slides, I see on YouTube the question about like if we have really a lot of access to a single piece of data, I would cache something maybe with a caching layer, Redis or something on top of Cassandra. So I'm not saying you not to use a cache, a HTTP cache or whatever cache. I remind you what cache also introduces complexity. So you have to be careful with cache. How you are going to invalidate that? If you have a distributed application, then how exactly you cache it? Do you go for distributed cache? Cache invalidation becomes much harder. So with cache, cache is a powerful technique, but it also comes with some costs. Now regarding a lot of reads, as long as it's not billions of read to a single partition, it should be totally fine. So Cassandra is not afraid of a lot of reads. As long as you can evenly distribute workload over multiple servers, if you have a lot of these celebrities, therefore you have them spread over multiple servers and you are good. So let's move on. Data types. So first of all, Cassandra features all the kind of the types you use it to have in different databases. Whatever integer, whatever boolean, whatever string, small int, text, and so on and so forth. Blob. So very typical set of different data types you use it to have. There are some unusual, like time UUID, but Artem, I believe you discussed time UU already, right?
Yes, indeed. We talked about time UID and UID, yes.
Yeah, good. So variant, varchar, so all the types like that shouldn't be a big surprise to you. So I don't want to spend too much time on it. There are some more types what can be interesting for some of the data. If you store some complex data types, you may be interested in collections. So set, list, map. With map, you can define internal types on your own. It can be text, int, text, int, and so on. So collection types must be pretty self-explanatory. You have this kind of data in any kind of a programming language, shouldn't be new to you. User-defined types, of course. User-defined type is an interesting thing. For a key space, you can create type of your own type. It's like a class in object-oriented programming. For example, address or bank account or whatever type is interesting to you, and define types there. And it will be your user-defined type, so you could work with that in the way you need. And for example, you can even store plain JSON as a UDT, and it will be stored as a user-defined type as long as it exists. Also, you could have some custom types, but that's in general pretty advanced strategy and very often not recommended. It was maybe a thing for Cassandra of older versions, but now all kind of required types exist already, so there is no need to make some more advanced things. Words are cheap, practice is golden. You will proceed with working with data types step, right? Artem?
So the data types will be more homework. This is part of your homework.
Okay,
If you
right.
want
It's homework.
get a
Sorry.
badge, yes. And
you are right. It's explained in our workshop. You've seen the explanations already. Please do it. Don't ignore. Do it. And then next one is going to be data modeling process. And I hereby give my microphone to the dear Artem.
Okay.
Let me switch my screen. Yes, it's your screen now.
Okay. Okay, so data modeling process, and here we started our Menti with normalization versus denormalization, and we said denormalization is not always good. Also in the relational world, people think about it as evil thing because it brings anomalies, right? You create multiple, you duplicate your data in multiple places, in multiple tables, and then you have to remember to update those multiple places to keep those duplicates consistent between each other. So more headache kind of thing, but and that's true. That's true. The everything comes at a price. Database normalization is a great thing. It's based on normalization theory. It's quite complex mess there if you try to actually look at the algorithms that decompose your tables to achieve higher normal forms and all of that. But why was it designed like that? Why is it important? Because at that time when it was designed, disk space was expensive. Disk was expensive, and you didn't want to duplicate your data. You wanted to store it more efficiently, and you would use joins and other operators like intersect and union to combine your data from different tables to compute the result. But now, so for example, in this example, we have employees and departments, two separate tables, and we have a foreign key. Department ID is a foreign key, which is key reference to a different table, to department's table. So we can find out that Edgar code department, based on this one, we go to a different table or join with this table departments and find that department name is actually engineering. So this is how relational databases work. But in case of distributed databases, joins can be very expensive. because the data, like we said, so what happened in a NoSQL database, distributed database, is that the record from or row from employees table is on one node and row from departments table is on different node. So to join them based on the foreign key, like relational databases do, you have to move data into some other nodes. You need to move it together on one node and then compute the result. That's expensive. Moving the data is expensive. So what NoSQL databases do, not only Cassandra, but others, and what, for example, data warehouses do, they use denormalization. So instead of storing the foreign key for the department ID, they will actually store the value that you may need in your query. If you need the department name, they will store it here. The problem is okay, engineering is repeated here twice. If we decide that we change engineering from the name of the department from engineering to the world-class engineering, then we will have to change it here in the departments table, but we'll also have to change it in the employees table multiple times. So that's why denormalization can be considered bad. So you have to remember, do these kind of things. And if we have time, we will talk about how to use batches to actually do these kind of things efficiently.
Yep.
Okay, so the modeling...
Sorry. I want to step in a little bit. It's one of very important topics. Could you please switch to previous slides? Yeah, this one. Good. So, regarding that's in general balance between multiple writes or more complex reads. With normalization, you go for more complex reads with joins. With denormalization, you go with more with bigger writes, multiple writes for one single update instead of one single update. There are some database developers in the world who are trying to claim like, yeah, we solved the problem, there is new SQL, which is great, so you can have your data distributed, but with joins. Sounds good, and even works on a very small data sets. So to build a join, you have to get all the data on the single node. Will it work? Yes, it will. When it will work? When your data fits into a single server. And then it's all great, but when you don't have to distribute it at all. So that's the biggest problem of new SQL, distributed SQL. It works, but only on a small data sets. But that is a different story. What I wanted to say, like what's most important for me in this story of a battle between normalization and denormalization. Well, there is no real battle. It's like a battle of a hammer and wrench. They don't battle. They have nothing against each other, you know. They're friends maybe even. But it's some people go for denormalization, some people go to normalization. You need to understand both. You need to understand then to normalize, then to denormalize. Only then you can be a senior developer, software engineer, and so on. Now, story, most important part of it. What is very different between write and read with join? Write in Cassandra is a single atomic operation, and Cassandra is very capable for writes, so you can execute multiple writes in parallel, even addressing different nodes, because, well, it's different tables, different partitions. It totally can be different nodes, so you can execute 10 write in a moment of a time, and it will be totally fine for your database, as long as it's a write-capable database like Cassandra. And you run them all at once, asynchronously. What's happening with joins? It's a little bit different story. There are very many cases then you cannot run all the joins at once. Mostly probably your joins will what? Depend one on each other. If you have multiple joins in a select query, it will have to first make first join, intersect and select some data on it, then get the second join, third join, fourth join, step by step, synchronously. All this time you will be waiting. So you cannot, in most of the cases, execute those joins simultaneously, and that makes a big problem. So although write is considered to be more expensive operation, with Cassandra write is cheap and you can run them in parallel. But joins have to be executed consecutively, and although select is in theory a cheap operation, it's getting much more expensive with joins. Then you have to wait for every next join to be completed before you can proceed. And that is a very important limitation, and that is a very important thing to understand.
Yes, but to add, there are actually distributed SQL engines, and just to, if you think about Spark SQL that you can run on top of Cassandra, and there will be some optimizations where joins will be computed in parallel based on subset of partitions on each node, and engines like Trino that will be able to do things in parallel as well. But another thing I wanted to mention, denormalization is used with relational databases as well for performance optimization. But here with Cassandra, this is what we do all the time. And going next to the approach, so frequently relational modeling starts with you completely focus on data and you model entities, relationships, and you normalize them. And only then you think about, okay, I need to execute this query, and currently I need to do 50 joins to do that. That's possibility. No, that's possibility. I wrote queries with 50 joins before.
I reached once maximum amount of joins allowed in MySQL. I got once exception. By the way, it's interesting to ask on YouTube. I see some people watching us of quite extensive experience. I just want them to guess, make a guess. Once in my life, I've seen an exception like you cannot use more than X joins in a statement. It was MySQL. It was around 12 years ago, maybe 10 years ago. I don't remember exactly. Would you guess how many was this number? It will be different for different databases. For Postgres, it maybe mostly probably will be different. Maybe it's changed to newer versions of MySQL. I don't work with it for many years already. What would be your guess? Artyom, and what do you think? What would you answer?
I think it was something like 64 or something like that. 128, I don't remember
Okay,
exactly.
so Artyom says 64. What would our visitors try? Okay, Vilas thinks 64. Okay. 60. Wow! Amit, you Googled it or you knew it?
61.
61. Right answer is 61. Can you imagine maintaining this query? That was such a damn nightmare. Maybe it was different database or different year, different version. Aditya? Yeah, for me it was 61, that's for sure. I remember this number. I would make a tattoo with this number. It was so much pain maintaining it.
But the thing is, with if you the relational database is one thing, right? But if you look at the data warehouses, people write those queries like every day with 60 joins, because it happens. Especially it happened to me not so far ago.
Yep.
But anyway,
data,
focus on data for relational data modeling, and then once you create the data models, then you will think about application, how your application is used, those tables, join them, and all of that. And then you will think, okay, maybe I need to create an index, maybe I need to denormalize here. And what's extremely important here also to understand is that it's not just one application. You design database once, it's relational databases are good and known as integration database. You design your database once and you can have multiple applications working with the same tables. They can join, they can do whatever they need to extract specific data. On the other hand, NoSQL databases, they are different. Usually design database specific to each application. So for each application, you will start with thinking about what your application will need, what type of data will it retrieve, what kind of workloads. You will of course get some idea of data there as well, because you cannot define queries without data, right? You will think about, okay, I need to retrieve sensor location, sensor value, the temperature value, and region, or things like that, the characteristics of a sensor. So you will, when you think about application, you also thinking about the data, but the data layout, the model of the data will be based on those queries primarily. So you will use the normalization there, you will use indexes as well in some cases. But the main point is you will design the data modeling is driven by your application, by queries. And with that, we will talk about this even in more depth. We kind of formalize it into a methodology. And I will show you a tool that implements part of this methodology, and we will be able to design our table. The tool design tables for us. We will just specify what kind of queries we want to use. So data modeling is actually could be quite complex process, because oops, yeah, I can leave. Could be quite complex process. If you start from scratch, you start from, you don't have data yet, you didn't think about applications, so you will have to collect data requirements, you will have to understand entities, relationship, cardinalities, keys, right? So what's going to be unique for that entity or for that relationship. Queries, how you're going to query, how you access your data, and access patterns involve queries, involve inserts, involve transactions, updates, deletes, and all of that. And only then you will be able to organize and structure. And after you organize the structure, you will produce some kind of database schema. You will optimize it with indexes, with the normalization, with bucketing, like dynamic bucketing, like we discussed, and so on. But usually, when people think about data modeling, they think about designing schema. Okay, this can be more complex than just, okay, well, let's start with these 5 tables. No, you need to do other things. But most of the time, maybe for when you join an existing project, you will look at the schema somebody designed it already, and that schema and data model is extremely important, especially for Cassandra, because you may have things like absurds, you may have all kind of, you may not be able to query because your primary key does not support that query. Efficiency, scalability, right? We need to distribute data correctly. We need to be able to sort the data in some cases. So we need to keep data consistent if we duplicate data in multiple places, and all of that. So I define these 4 data modeling, very general, high-level data modeling principles. You need to know your data. And some of the most important things, it would be keys. You need to understand keys and cardinalities. Like network may contain many sensors, but sensor must belong to exactly one network or not. It depends on your requirements. Maybe the sensor, like a cell phone, may be reached by 2 towers at the same time and belong to 2 networks. Okay, so this is all something that you need to understand before you do data modeling. Know your queries. You need to know how you query and access data. Nest data, it's essentially that denormalization that we talked about, right? So we're going to nest multiple rows in the same partition, or we will create a collection, a set or list or map to nest that data. So that's kind of denormalization. If you think about it, it breaks the rules or normalization theory rules, right? So that's nest your data, and some NoSQL database actually, like document databases, JSON, I think they use the term nest data before they use de-anonymization. And duplicate data, it's better to duplicate than to join, right? So to support different queries over the same subset of data, you will have to organize that subset of data differently in different tables. And by doing that, you will duplicate your data. So to make it a little bit more formal and repeatable, as you will see, it's possible to even automate this process. This is the methodology in a nutshell. We need to understand the data, identify access patterns, apply the query first approach, optimize, and implement. Okay, so by understanding the data, we are going to do the conceptual data modeling. One way to represent it graphically is using entity relationship diagram. To identify access patterns, we will do the application workflow model, and we'll use application workflow diagram. So why it's just so the application workflow, you will see an example. It involves queries because it involves tasks that are supported by queries, because we design application data-driven application at some. So we have the workflow that queries our database, and at each step in that workflow, we know which queries we already executed and which type of data we already have. And then these two will map into logical data model. One way to represent it would be using Chebotko diagram. I will show you an example. And logical data model still can be analyzed and optimized and implemented as a physical data model. And we will see physical level Chebotko diagram and CQO implementation as well. So 4 objectives: understand data, identify access pattern, and so on. 4 models: conceptual data model, application workflow model, and 2 transitions: map and optimize. What is most difficult here is, I would say, the most difficult here is, if you're doing it by hand, then map and optimize and conceptual data model properly. With the map and optimize will be the most difficult. If you're using a tool, then you literally, the mapping will be done for you, and maybe even optimization in some cases. So this is the first step. We need to design conceptual data model, application workflow diagram concurrently, or one after another. Which one is first? It's hard to decide, because you need to some understanding of data before you can design queries. But in any case, this example of the conceptual data model that we already used in the previous workshop. We have networks can have many sensors. Sensors record temperature, so each sensor can record has many temperature values. Each one will have a timestamp. And sensors have ID, location, latitude, longitude. They have some characteristics. Network has name, description, region, number of sensors. Network has name as the ID. Sensor has ID as its identifier. And temperature doesn't have enough attributes. It's a weak entity type. It doesn't have enough attributes to define a key. The key is, there is a partial key timestamp, but also has to borrow the ID from the strong entity type from sensor. So you need to uniquely identify the value of the temperature. You have to have both ID and timestamp. So this is how to read it, and I will not spend too much time on this right now. So this is an example of application workflow diagram. There are 4 tasks here. They are annotated with specific data access patterns, like finding information about all networks and ordering by name, finding hourly average temperatures for every sensor, and so on and so on. And then you can see, because each task queries database, we need to support this query. And how will we support this query? We will design table for each task to support this query. Usually one table supports one query. but not always. There may be multiple queries that are useful that are supported by the same table. So
Sorry, May, I would like to step in here for a moment. There is a very important point. Could you please switch to a previous slide? Yeah, right. Like that is an application workflow diagram. It describes how customer access your application, uses it, wants to see in which order what, and so on. How do you build this? It all comes with experience, of course. But for me, easiest way to step in and start designing application workflow diagram was my previous experience with user stories. Maybe you have heard something about user stories before. Remember, like designing application or designing test cases, I am start to think like as a customer for what? For maybe buy something later. I push the button to include some particular thing into my watch later or buy later reminder list. Like imagine we are speaking about e-commerce app like in Amazon. And this approach, user stories as customer to do as user role to do something, I do following steps. A very simple approach. And with this approach, you can easily analyze your application. Your some scientist working with this data of sensors doesn't think this way, but we have to structure steps he or she will have to do in order to reach the data. What I need to, what as a customer, as a scientist working with scientific data, temperature data, I want to do something. I want to see history of the temperatures on a particular location or from a particular sensor. That is going to be my primary query. And then I start to think, so that is a goal of my customer at this moment in this particular case. But how do I show temperature values for a sensor? In order to show temperature values for a sensor, I need to know which sensor we are going to work with. Do you think your users remember IDs of your goods or whatever videos on Netflix? Of course not. You cannot just go and show a video on Netflix. You need to know its ID. Okay. Then, in order to give some choice to our customer, to our scientists, we have to do what? Display all sensors in the network. When we show list of sensors, he or she can click on the particular one and get a result. And here you find very interesting thing. We use it to think what software has dependencies, like your Python application depends on some library, or your JavaScript application depends on half of the world, at least according to the size of node modulus folder. But the story is workflows also have dependencies. You cannot show temperatures as long as you don't show something what will allow us to get ID of a sensor. And then to show sensor networks, sensors in the network, you need to show sensors. And here we identified workflows and dependencies between them. And finally, in order to see it all, I have to log in. So here is going to be a Q0 actually on this workflow, hidden for clarity, what we will need to compare email and password and make customer login.
Yes, absolutely. Thank you for the explanation here, Alex. So the next step would be designing logical data model, and how you design the data model, logical data model, based on the queries you already define in application workflow and based on the data and keys and cardinalities that you defined in the conceptual data model. So there are some basic rules you can follow when you're designing those tables. I call them mapping rules, and there are 5 of them. So the first one is based on conceptual data model. So the query that you're going to support will involve some entities and relationship from that model. So the entity relationship types will become tables, and the attributes attribute types will become respectively columns in those tables. So this is the first rule. The second one is based on the next three are based on the query. So the second one, equality search attributes in your query predicate will become the beginning columns of primary key. They will form partition key and possibly subset of clustering key, or maybe just partition key, but they will be in the beginning of your primary key. Inequality search attributes will have to be clustering columns, because that's the only way we can do inequality, greater than, less than. And ordering attributes will map to clustering column, because that's the only way we will be able to sort data in Cassandra. And the final one is usually where most people stumble with, they have difficulty with, and design incorrect primary keys, is this key attributes. Key attributes from conceptual data model. They will have to be part of the primary key in your table to maintain uniqueness. Okay, and those keys are, of course, so for entity types, usually easy to define the key, but you need to also define for relationship types, and they usually not even shown on the diagrams because they can be derived. So let's see an example how we can apply this rule. This is a query 5 that was not, I specifically made a more complex query so you can demonstrate all 5 rules. That's the same subset of our conceptual data model. Sensor records temperature, and the new query find raw measurements for a given location and a date time range ordered by timestamp descending. So obviously here we creating all of these subsets. So we basically creating this relationship that involves sensor and temperature. And we call this table temperatures by sensor. And we are going to need value. We're going to need latitude, longitude, and timestamp. So that's the mapping rule number 1. Mapping rule number 2, equality search attributes from our query will become the beginning, the prefix of our primary key. They will form partition key completely or part of it. So in this case, what do we see? Given location, okay, given location, date time range doesn't count. It's not equality, it's inequality. So given location is latitude, longitude. So latitude, longitude become the partition key columns. And I see there is a network problem in the chat.
Yeah, looks like some network is lagging somewhere today. We cannot change it anyhow right now, so I hope it's just not too bad. We have to proceed, yeah.
Yeah, I can hear Alex in real time, no issues at all.
Yeah, so mostly probably
no
it's between me and Restream, or between Restream and YouTube. Or maybe Restream server.
Yes, sorry for that. So continuing with this example, latitude, longitude will be either both of them will be partition key, or one of them will be partition key, the other one clustering column, but they will be in the beginning of the primary key. In this case, both of them, I decided both of them location will be partition key. The next rule is going to the inequality search will become clustering column. So date time range is our timestamp. So we adding timestamp here as a clustering column. It's ascending order because we don't care about order yet. And the next rule, rule number 4, says that if you need to order, right, the ordering attributes will have to become clustering columns, and you need to use correct order. Sorry, correct order. So in this case, when we apply mapping rule 4, we get the clustering column descending order in this case. And then the final rule says that we need to make sure that the key, in this case, key of this relationship, is preserved in our primary key. So we still need to add sensor to uniquely identify our value, right? It's location is how we want to retrieve the data, but the value is uniquely identified by sensor and timestamp, right? So we still need to add the sensor. And this is a last rule that most of the time people make error here, forgetting this sensor. But this is how to apply that. We can actually do this example in our data modeling tool later and see how it constructs this type of primary key for us. So following these rules, we can support our queries by designing this logical data model with tables. We have the sensor byte network table that we used already, and we applied, as an example, dynamic bucketing on this table. But this is how it looks like. And for the sake of time, I will skip description of each table, but I will show you later them in the data modeling tool. So, and the final step is to optimize and implement the result in Cassandra, using Cassandra query language. So in this case, what kind of optimizations? So probably the five most common ones are here. The partition size is split in large partitions, and we kind of already discussed it with dynamic bucketing and with large partitions, hot partitions, spend a lot of time on that. And data duplications, and maybe you can use batches sometimes to solve the problem. Indexing and materialized views, will we use them, will we not use them? What are the pros and cons? Concurrent data access, if you have multiple multiple user, multiple applications changing the same value, is the change idempotent? If will there be any conflict, right? So if we have time, we can discuss that, or maybe discuss in a separate workshop. But lightweight transactions is one way to solve that. And dealing with stones is also an interesting topic that we probably not have time to talk about today. So there are actually three optimizations that were applied here on physical data model. First of all, what's the difference? You have data type specified, but also in green here we have the highlighted the optimization that we applied. Since we want to retrieve all the networks, we put all of them into one bucket. So we can only access one bucket on one partition. This is the optimization. Instead of storing each network in a separate partition, we store all of them in one partition, so we can retrieve them as one partition very, very efficiently. Two optimizations here. Date and hour were combined into one column. Using dates separately and hours separately, we're just using timestamp and storing them together. And also week was added as part of the partition key. And you probably know why, to split the large partition, because if we don't add any time component into partition key, then our partition grows over time, and it will become a large partition. And finally, implementing these tables in CQL should be quite straightforward. These are the same tables and with data types, with partition, clustering key, primary key design. So one of the things I wanted to mention here to wrap it up with this approach or methodology is that what's the difference actually between relational data modeling and Cassandra data modeling? Okay, and you can see these two methodologies, they have some things in common, like you can use conceptual data model design in both of them. But the big difference is that you do not use normalization theory, and the queries in relational approach. So you do conceptual, map it to relational, logical, then normalize it, get normalized, and then you do physical optimizations. That's when your physical optimization, that's when your queries are used, that when you decide, okay, I need to create an index here, or to support specific join or select. And I also need to maybe denormalize because this join is not performing as fast as I wanted to, and things like that. In case of Cassandra, there are fewer steps, and actually, I would say it's a simpler methodology, even so it's not the easiest one, right? But you can see this. The queries will be used right away to design your tables, and there will be no normalization, right? So that's a difference. And with that said, I will show you KDM data modeling tool.
Which one is great?
Okay. And it's part of the our, again, GitHub workshop the README file. So you can, the tool itself, you can just open it online and you can download the XML file, which is a project file, and you can follow me, follow what I'm doing. But I will show you first. This is just an empty project for the KDM tool. There is nothing defined here, but I will show you how to do it. So it's not that difficult. So we will try to do our just one relationship, just to see the process. So we had the network, and we have sensor, okay, and we have relationship network. Let's say has sensor. We will connect them. Okay, we will say the network can have many sensors. So I will annotate with many, and each sensor belongs to one network. I will annotate. Now I need to add some attributes. Let's not get too crazy. Just add a couple of them for each one. So there will be name of the network and description, and ID of the sensor, and say description. Okay, let's connect them to, did I connect it right? Did I not? Let me check. Yes. Okay, and then we need to designate key attributes. So right click, this is gonna be our key for the network. This is gonna be ID is gonna be key. Okay, so this, let's go to the next step. Access patterns. We will only use one. Just want to show you how to do it. So as a just a simple tutorial. So let's retrieve all sensors in a network. We had a query like that. So what we want to find is the sensor ID. So find sensor ID and find description. And what is given is the name of the network. Okay, given name. And at this point, we can click logical, and this is a table that is generated for us. Given the name of the sensors, and this is by network, the name of the network, we can find ID and sensor description. Okay, and we can continue and generate physical. Decides, okay, ID will be maybe this time it will be UUID, and then CQO, and finally we have the table that we can use.
Yay!
Right? Yes. What happens if we change the cardinality? Why cardinality is important? Let me say the different cardinality. I will regenerate the, well, not in this, not for this query. I will also need to change the query. Anyway, let me show more complex query for you with the actual example that we have in the slides. Okay, so this should be familiar. Network sensors. These are the 4 queries that we defined in this tool and also in our model that we already discussed, right? The finding information, about all networks, finding hourly average temperature, finding information about all sensors, finding raw measurements, and all of that. So all four are defined. We can generate logical, and sometimes we will have a choice, right? We can choose one of these tables, for example. So and usually the choice is because of the ordering, like ID and date change the order, or maybe date can be just clustering column, or ID can be clustering column. You can choose which one you like, similarly as before, and generate physical, generate SQL. But let me show you some more complex query. For example, what about what if we want to retrieve this? So let's create a new query, query 5, and let's say we want to retrieve all the raw measurements from possibly multiple sensors from multiple networks based on the region. Okay, so we're gonna want to find this value, and we will retrieve based on the region information that's given. Okay, so what type of table do we need for that? Let's see. Okay, so this is query 5. Given the region, we will retrieve the value, but we will also add timestamp and sensor ID as the clustering key. And the order is not really important unless we want to sort. We probably want to sort based on timestamp. So this is how easy you can design a table using a tool. Basically automates this design. And if you notice, not even network name is used as part of the partition key. And the reason is because the key of this relationship is sensor ID. Sensor can belong only to one network. If we change that, we probably will have we should have, I would say, name becomes part of the clustering key. So this is the end of this demo, and we are actually very close to the end of our 2 hours. So at this point, I would say we will skip all the optimization techniques and we'll wrap it up, Alex.
Yes, we anyway have it in the primary course, so that is an introductional level series, and you get deeper in the Academy Data Stacks course, Data Modeling DS220 at the Academy, and it's the only right way to get ready for the certification. So let me switch to my screen back in a moment.
And the tool is free, and as you may guess, it's designed by Dr. Kashlev, who is a professor in Eastern Michigan University.
That is pretty cool. So, switching to my screen. Yep, good. Okay. So yeah, love this tool. I'm with you, Cedric. It's totally great thing, absolutely great thing. It helped so many people. Oops, it helped so many people. That is absolutely amazing. Good. So what's next? We will have a quiz. So if you didn't win prizes last week, now you have chances to do it. But before that, places for you to know. Datastacks.com learn data modeling by example. That is a very important thing, and that is a thing what like very well explained many cases, explanations done by Artem. Cassandra data modeling exercises are available at Killer Coda by the link above. We are at your disposal at the Discord server, so we can answer questions there. Some more cases and interesting readings we also could. I don't know if I can copy link address and send it to the chat. It may be a very interesting reading. Yes, I can, which is great. Don't forget to do the homework, submit the homework form, submit the homework with screenshots, and get your data stacks modeling workshop badge. But what is better than badge is a real globally recognized certification, so don't forget. Data stacks offer more than just this workshop. You can get your education, training, and certification totally for free with data stacks developers. Discord community I already mentioned. Discord, I will not be there next week's, but our data stacks developers will be, so they could help you. Your instructors, Artem Chibatko, PhD, data modeling methodology author, and me, developer advocate lead at DataStax, Alex Volishnev. Links on the screen are for you to add us on LinkedIn. So it's very easy. Type jump, add us, and we will be happy to have more friends there. And finally, you cannot wait for the quiz, I guess. So let's go. If you are not on Menti yet, then jump in right now because we are short on time. So quiz starts in some seconds. To join the quiz, you can enter the code 14095206 on menti.com, or you can scan the QR code on the screen. And oh, I see. Artyom hides the code a bit. Sorry, it's on my side. But again, code is 1409, or I can just call for Menti on the YouTube chat. Good. So I hope you are in already. One hint I want to give you, as you are so great people visiting our workshop already, not the first time, most of you, I want to give you a little hint. YouTube has a little discrepancy, a little lag, a little delay. So answering questions, you better watch not YouTube stream, but Menti screen, because it will be a little bit ahead, so you have more chances to get more points and get closer to your victory. From this point, I see people joining. I hope you all are good. Very last moment to join, very last moments to get chances to win prize. And let's start. There will be 8 questions. Answer fast to get more points. A Keyspace. A Keyspace is organized into rows and columns. Keyspace contains tables and sets replication. Keyspace is the base unit of access. Keyspace is a place to store extra house keys. So, you are answering quickly. I see most of the attendees already voted. And with the last few seconds, will we have any latecomer? And time is over. So, most of you made it right. Keyspace contains tables and sets replication. Partition is the base unit of access, and organize it into rows and columns as a table, not Keyspace. Who was the fastest this time? Bran the Broken made it with 982 points, which is incredibly fastest hand on the West. Question number 2. So answer fast to get more points. What's a partition key? You were paying. Is it an optional column to allow group by? It's maybe a column to define partitions required. It's maybe a required column to set sorting order. Or is that the key to all the doors? Yes, partition key is a column to define partitions. It is required. It's not to set sorting order, but to set partitions. Well, who was the fastest this time? Praveen was the fastest, keeping the first place. Nitesh on the second, and Sumit on the third, with Mr. Wonka and Rita with a couple of points difference of places, number 4 and 5. It's not over yet, we are just starting. So let's go to question number 3. And answer fast to get more points. Table can have many rows per partition. True, false. It requires special Cassandra YAML configuration. It's illegal. What do you think? Is it correct, wrong, or maybe special? It's totally legal, and that's perfectly true, and everything is fine. It does not require any special configuration. Okay, so was anyone faster, Miss Praveen? This time, Sumit was faster, keeping the third place, but Praveen still on the first one. By the way, I know there are people, there is a conference in New York right now, API Days New York, and I know they are watching us. I'm very curious if anyone is joining our quiz from API Days New York. That would be very interesting. Question 4. So let's see what will happen. Answer fast to get more points. In Cassandra tables, which are required? Data columns, clustering columns, partition keys, user-defined types. What is required in Cassandra tables? I should have added a question if NoSQL is schemaless. That's pretty sad I didn't do it. That would be a good filter to those who paid attention. Partition keys, right? Partition keys are required. You can safely omit clustering columns if they're not required by your data model, but technically only partition keys are required. Okay, so there are no mistakes between leaders, but looks like Amit was a little bit slower this time, and Praveen was fastest again. So no changes in top 3. And that is going to be question number 5. So answer fast to get more points. Inequality predicates are allowed on all table columns, partition key columns, clustering key columns. No inequality predicates are allowed. Okay, people giving their answers. But time is up. Right answer, inequality predicates are allowed on clustering key columns. On partition keys, you cannot have any inequalities, only equalities. So, Sumit and Giacava make a mistake. That means what top 3 will change right now. With Nitesh fastest jumping on the first place, moving Praveen down to the second, and Mr. Wonka makes it to the third place, with Tiger Baby very, very, very close. Mr. Wonka, you can hear he's breathing like somewhere from behind. Competition is not done yet. Okay, let's go. Question number 6. Samid, keep fighting. Answer fast to get more points. In the data modeling methodology, we start modeling with physical data model, logical data model, conceptual data model, and application workflow, copy-paste from Stack Overflow. Time is up. And most of you made it right, conceptual data model and application workflow to map them into logical data model, which is the wrong answer. And physical data model is one of the latest steps from the data modeling methodology. Like we have a guest here, like you have, and Mr. Wonka makes a mistake just right after getting into top 3. Oh my god. Praveen returned to first place with Nitesh on the second, and now Tiger Baby on the third place with Amit on fifth and Kevin on fourth. It's almost done. Question number 7. Answer fast to get more points. Primary key defines row uniqueness. False. Correct. Primary key is deprecated. Let's see. Amit says what question 6 appeared in the first workshop as well. Yes, and that is an intention. I want you to remember the steps. Correct. Primary key defines row uniqueness, and that is a totally correct statement. So, who was fastest this time? There are no mistakes, but who was fastest? Looks like Nitesh was fastest. Very well done. Praveen and Nitesh made no mistakes so far, and Tiger Baby is on the third place with 1 mistake. And Kevin P is now 50 points behind Tiger Baby, which is nearly nothing. That is the last question. So, you want me to push this button, right? Okay, let's go. Answer fast to get more points. How does Cassandra perform joins? Cassandra joins require a joint table. Just like SQL joins, Cassandra does not support joins, or Cassandra only joins good clubs. Time is ticking. Most of you made their step already, and correct answer is Cassandra does not support joins. Cassandra joins don't require joint table. It's not a thing. It doesn't exist. It exists only in my imagination. It's not like just SQL joins. SQL joins are totally great, but they don't work on big data. Okay, they work on big data, but very, very slowly. I better say it this way. If you have a customer-facing database, you cannot afford joins on Cassandra. Cassandra simply does not support joins. And Kevin makes mistake, but that doesn't matter because Praveen, Nitesh, and Tiger Baby made no mistake. Nitesh gets overtaking Praveen again, gets to the first place. Very well. So, we congratulate Nitesh, Praveen, and Tiger Baby. Please make a screenshot of your winning screen with your position, number 1, number 2, number 3, and send it to me on LinkedIn using https datastux.io/Alex. Nitesh, congrats! And I will take care of you getting the prizes. Now, those who are on the leaderboard, congrats. You made it very well, even though you didn't made it in the top 3. But remember, we will have a next workshop soon, 3rd workshop of this series. So don't be disappointed. We will have one more chance at our next workshop. By the way, I think next workshop will be not next week, please notice that, but next week. I believe it's going on to be next week. Have to check the schedule. And finally, if you are not even on a leaderboard, most important thing we are giving today, not the prizes, also they are fun, but actually knowledge, because it's in 2 weeks. So next on 10th of August. Thank you, Cedric. And knowledge is much more valuable than our swag. And then finally, make a screenshot. I'm changing the page. If you didn't still contact me. 2 questions. How do you like this workshop series? Would you recommend it to your friends? It's a quick choice. Okay. Looks like first answer was very quick and very positive. Thank you so much. I see like a very good score after all. I'm sorry if you rate it not so high. I hope you will improve for the next series. But I know, you know what? You stayed with us till the very end of a second workshop. You spent with us almost 5 hours overall. That means you like it. Admit it. Like, I know it. And by the way, don't forget to like and subscribe on us on YouTube. And then finally, what would you suggest? Any feedback regarding this workshop or this series in general? Just specify, please, what exactly you mean, because it's a second workshop in this series. I will keep this window open, so you can write your feedback after the workshop. It will be open for half an hour more. And let us switch to the last slides. Don't forget to complete the homework. We explain how to do it in our GitHub repository, which you have seen already. Join Discord if you will have any questions, or catch us on LinkedIn. Links are on the screen. Homework, right? Yeah, homework, actually instructions are configured by Cedric. Thank you. With that said, that was Alex and Artyom. Thank you so much for joining. It was a real pleasure to work with you and many good questions today. And I think we are done. Artyom, do you like to add anything?
No, it was great. Thanks for coming and hope to see you during the next workshop.
Yes.
I will be in the chat.
Great. See you then in 2 weeks. Thank you, Katie. Thank you, everyone. Thank you for joining. Nitesh and our winners sent me a message on LinkedIn. And then meet you soon. Thank you, Rita. Thank you for coming.